201, cost-effective, true random bit generator using parallel robust Signum-Based chaotic maps. Still something.
Yes. Good afternoon, ladies and gentlemen. Vimon Sanom. I'm from Thailand. It was a long journey from Thailand to here. I took about more than 20 hours from my country to be here. It is very nice to see everybody here. And it's my pleasure to give a presentation on a cost-effective true random bit generator using a pair of robust Signum-based chaotic maps. Well, the first question I would like to ask everybody here is, what is a true random bit generator? The true random bit generator, or TRB, is typically defined as an algorithm or some devices that enables the generation of random digital sequences. Of course, they're commercially available like IBM's or Quantis or Sun Crypto Accelerator 1000 like this. But these are very expensive because they use the quantum techniques to generate the random number, or we call these techniques are stochastic system. And why we need a true random bit generator? Of course, we use for the security issues for cryptography applications like the Lena here. We encrypt, we get this scrambled picture on the text, we get the ciphertext like this. So the true random bit generator is very important for this kind of applications. Of course, how to generate true random bit generation in the existing techniques. The first technique is the quantum noise amplifications, of course. For example, the electrons, when you, like in the resistor, when you supply the voltage, the electrons might vibrate and it generates noise. So we use that noise and then you amplify it and threshold it. You're going to get some kind of random bits as well. And the second one is the digital techniques, of course. Well, it seems to be easier and cheaper than the first techniques, but it's very complicated. You need at least like 8 flip-flops to generate. Well, there's a limitation. For the quantum noise amplification, the system is very expensive, requiring many devices. But for digital techniques, are you sure? It's not guaranteed, okay? And large number of flip-flops are required. That's why I propose the chaos-based true random bit generator. But before that, I would like to tell you why chaos theory can be used for the true random bit generator. Let me tell you about the chaotic system. Of course, when we talk about the linear system like this, everybody could guess the answer very easily because you can get the equation very easily, right? But for a nonlinear system like this, like a clouds or like this one, it is very difficult to find the equation. So, chaos theory gives you a deterministic system. It's a dynamic system that can be represented by equation. And there are 3 natural features of chaos. The first one is a deterministic nonlinear dynamic system. That means in your equation you must have at least one nonlinear terms, and it is very sensitive to the initial condition, okay? And the third one is the random output values, unpredictable. There are 2 kinds of system I would like to give you here. One is the chaotic maps, or one-dimensional system. For example, the well-known logistic map like this. It can be written in this equation. You could see that the output in time domain is random. And if you see focus on the bifurcation like this, okay, you could see there are some regions, the thick regions represent the chaotic regions, but there are some kind of, white region here. It is not chaos, okay? And the next system is the chaotic flows, or the 3-dimensional system. For example, a well-known Lorentz system, or I think somebody ever heard about the butterfly effects, right? So it is represented by the ordinary differential equations for the 3 system like this. And you could see that the trajectory or the space of this system looks like a butterfly, okay? And the output is random as well. Well, for this system, when you put this kind of ordinary differential equation into some programs like MATLAB or Python,